Right, good morning. So welcome back to the last week of classes. Today we are going to be talking about machine language. Before starting in on that, wanted to kind of just briefly talk about the final exam. As you know, we have been planning to hold the final exam in person, pencil and paper, that kind of thing. Obviously, facts on the ground are, as they say, evolving rapidly. And so right now, we are very, very seriously considering switching to a take-home exam kind of online. I can see that nobody here is in favor of this. So probably, it's going to be the same sort of deal as the midterm, that you will have a block of time during which you can take the exam. You will have 3 hours to complete the exam during that time. Like I said, we haven't, we're not quite ready to call this yet, but at this point, this is kind of the way I'm leaning. I don't want to keep you in suspense for too long. I promise we'll make the final decision like in the next day or two. And definitely let you know kind of what's up with that. So, meanwhile, machine language. What is a machine language? So a machine language is sort of the language that a machine, namely the CPU inside a computer, natively speaks. So there are many of these machine languages, basically just as many as there are machine architectures, where an architecture, or more specifically an instruction set architecture, is sort of defined by how the chip itself, the microprocessor, is designed. How many registers? What hardware is there for executing different instructions? What instructions is it capable of executing? And then you put all of these kind of together, and every machine architecture has a machine language defined, which is sort of a very compact, succinct encoding of what are the individual instructions that that machine is capable of executing. And there is dedicated hardware, in other words, dedicated circuits within the microprocessor for understanding and decoding this machine language, which is why it has to be relatively simple. I mean, this is the kind of conceptual difference between assembly languages and machine languages. Assembly languages, we may think of them as kind of very simple and dumb, but they're not simple and dumb enough to be executed directly by the hardware of a chip. And so the whole point of machine language is to take all of the information that's in an assembly language instruction and encode it down into individual bits in a fixed length, or some of these are variable length, individual bits in a machine language instruction. So why are we studying this in the first place? Well, a big part of the motivation is to be able to do something kind of interesting in assignment 6. So far, we have looked at part of assignment 6, where the goal was to just replace the return address. But now, we're actually going to be looking at the next part of assignment 6, which is about really exploiting a buffer overrun by actually writing your own instructions to be executed as part of the exploit. And to do that, you will need to sort of understand the details of ARM64 machine language. So we're going to look at that motivating example. We're going to look at the details of ARM64 machine language, go over a bunch of different instructions, exactly how they're encoded. This is not intended to be a complete exposition of the ARM version 8, ARM64 machine language. Despite the fact that it's one of the simpler machine languages out there, it still has a certain amount of complexity, and we want to expose you to sort of just enough of that complexity for you to be able to do assignment 6. And then on Thursday, we are going to see exactly how the assembler generates machine language from the assembly language that you write. We're going to see how it sometimes can't do the job completely and needs help from the linker in order to finish the job. And we'll look into how the linker operates and how it finishes that job of creating machine language from assembly language. So that's the agenda for the last 2 lectures. So let's go back to last week when we talked about assignment 6. And we sort of talked about once you are able to smash the stack, once you are able to replace a return address that is placed on the, within a stack frame, you can cause all kinds of damage. You can do all kinds of things to exploit that situation. And we looked at a relatively simple thing last time, which is just replace that return address to point to existing code. But we mentioned this possibility of going beyond that, of doing something more interesting, namely arranging for a bit of code that you create to get stashed somewhere in memory, and then redirecting that return address to point to that, to those instructions that you want to execute, even if they're not in the original program. And basically, we did this by exploiting this unchecked write to a fixed length buffer, overflowing that buffer, and therefore overwriting parts of the stack. So now let's look at exactly how we would go about doing this. Well, so let's kind of try to study what's going on here. We see that we have a couple of different things going on. We have this local buffer called buff in the stack frame of read string. And that is the buffer to which we have an unchecked write. So as this program is reading information from standard input, it is writing it to that buffer. It's not checking whether it might be overflowing that buffer. But then read string does something else. It actually takes what it read and copies it to a different array, this array called name. And this, in fact, is a checked write. So the loop that copies buff to name actually only goes as far as buffer size. So it's only going to copy a fixed number of bytes there. So no exploit there, but we're actually going to be relying on this particular copy in order to get the code that we want executed to live not on the stack, but in the BSS section of memory. That means that it is long-lived, and that means that once we do this disabling of certain protections that I talked about last time, we're actually able to execute code from that section of memory. So let's look at how all of this is going to shape up, how memory is going to lay out. So here we're looking at sort of memory maps of the stack section on the left and the BSS section on the right. In the stack, we have a variety of different stack frames. Lowest on the stack, that is at highest memory addresses, we have the stack frame corresponding to main. Above that, we have this function called getName, its stack frame. And then eventually above that, we have readStrings stack frame. And there's, some stuff in that stack frame, various local variables and things like that, including space allocated for this buffer. Remember that buff within readString is a local variable, therefore it is allocated on the stack. So the stuff that we type in or send in on standard input into our creator program is going to wind up there. On the right is the BSS section, where, again, there's some stuff, including space for this array called name. Okay, so this is kind of the initial state of the world when we start executing the greater program. Once it gets into that read string function, starts reading stuff from standard in. Now, what do you want to wind up in buff? Well, first, you actually want to write your name and a null character, just as in the B exploit that we talked about last time, so that in the end, the greater program can print out, hi, your name, your grade is blah. But now there's kind of, hopefully, some space left over in that buffer. And what, in fact, you're going to do is stash those instructions that you want executed later on, the instructions that are actually going to execute an attack and perhaps give you a grade better than a B. Those instructions are going to go past that null byte on the stack in read string, with the hope that eventually they will end up in the name array. Now you go ahead and you smash the stack, you insert whatever additional padding you need, you get into getName stack frame and override the return address that lives there. And what do you overwrite it with? Well, you actually are going to overwrite it with an address in the BSS section where you know the instructions that you included there are going to end up. Okay, so that overwritten X30 is going to point into the BSS section where eventually, those instructions will get copied, smash the stack, execute the code that you want to execute, which, probably is going to figure out where grade lives in memory, overwrites the grade, gives you an A instead of, a D or a B. So this is how this exploit is going to work. Questions about this? Yeah? It doesn't stop copying when it reads the null byte. Look at how the code is designed. It actually copies a fixed number of characters. Look at that last for loop down there. It's not a string copy. Probably it would be better for the security of the program if it were a string copy, kind of marginally better. But that's not what it does. It copies the entire buffer, buff size bytes. Okay? Yeah? The buffer size is given to you. It's just an enum in the code, or I think it's an enum in the code, yeah. All right, and so the last remaining question is, well, what do you put in that region of memory? Well, you need to put the instructions that you want executed. In particular, you need to put the machine language version of the instructions that you want executed, hence the rest of today. Okay, so let us move on and talk about the AArch64 machine language. Now, if you took COS 126, you might recall that you did something vaguely along these lines when you talked about toy. You saw a layout of an idealized machine language where there was a set of bits that were divided into different functions. Some served as an opcode, operation code, tells you which instruction this is. There might be some indicating which registers the instruction uses. Or there might be some format that actually includes addresses or other just binary values that you encode as part of the instruction. Well, what we're going to be doing here is the same kind of idea. We're going to look at a variety of instruction layouts that are defined by the ARM 64-bit architecture. They're going to be messier than this. Sorry, nothing we can do about that. It's just the way the architecture is defined. But you're going to see a lot of the same features. Some bits are going to be dedicated to telling you which instruction it is. Some bits are going to be devoted to telling you what the instruction is operating on, whether that's registers or immediate values or offsets or addresses or whatever. And there's going to be kind of a well-defined layout where the hardware within the machine always knows that it can check this set of bits, and that's exactly telling it, what the destination register is. So the machine language that we're going to be looking at has a couple of characteristics. One is that all of the instructions are exactly 32 bits long. Now, this isn't the case for, let's say, the x86, the Intel x86 64-bit architecture, the one used in Windows machines and things like that. That is a variable length instruction format, where some instructions are 8 bits long, and some instructions can get up to, what is it? At least a dozen bytes long. I mean, they can get pretty massive. So variable length depending on which instruction it is. Not the case here. All of the instructions are 32 bits. All of the instructions have to be 4-byte aligned. That means you can't have an instruction in memory that doesn't begin at a memory address that's a multiple of 4. Okay? And that leads to some simplifications in the hardware. And in fact, it also affects the design of the machine language a little bit, and we'll see some examples of that. So some bits are going to contain the opcode, some bits are going to specify registers. Like I said, other bits, are going to contain different things. So the rest of today, we're going to be doing something that is going to cause you to fall asleep. It's going to be pretty dry. We're going to be looking at instructions. We're going to be looking at them bit by bit. I do not expect you to stay awake. I do not expect you to remember all of these, memorize all of these. What you're expected to do is understand the general concepts and then be able to refer to these slides and refer to the documentation of the AArch64 machine language that's provided on the website as you're working on assignment 6. So unless I did something really, really wrong, all of the instructions that you're actually going to need for assignment 6 are on these slides. So that's going to be kind of a shortcut to wading through the, 1,748 page instruction set reference. In general, the instructions are going to look kind of vaguely sort of like this, where the first thing the hardware does is it looks at a fixed set of about 4 bits to tell it which group of instructions we're talking about. This isn't even the entire opcode. This just tells it kind of how should I interpret the rest of these bits. And there are a few main classes of instructions. Some are going to be good old manipulation instructions, ALU instructions, that take 3 registers, 2 source registers and a destination. There are some others that are going to take 0 or 1 source registers and an immediate value, that is a constant value that's actually encoded in the instruction, together with a destination in register. We're going to look at branch instructions, both unconditional and conditional branch. And we're going to look at a bunch of load store instructions. And each of these is going to have a layout of bits, an interpretation of bits that works a little bit differently because of the difference in the nature of the instructions and how many registers it needs to know about, and what kind of additional information it needs to know about, right? When we talk about conditional branches, obviously you need to know which condition. Is it less than or equal to? Is it greater? Is it not equal to? So there are going to be some bits dedicated to encoding which condition you're worrying about. So we can start drilling in on each of these categories of formats. The first one we're going to talk about is processing, or ALU instructions, that take 3 registers, 2 source registers and a destination. And this is the layout of bits. The first source register is always going to go in this set of 5 bits, marked in green. The second source register is always going to be this set of 5 bits. And this makes sense because there are kind of 32 general purpose registers. And the destination register is going to be the lowest order 5 bits. Now, a little bit of terminology. Here we are numbering the bits using a pretty common convention where the least significant bit, that is the bit all the way at the right, the ones place, if you will, is called bit 0. And because this is a 32-bit instruction, the bit all the way at the left, the most significant bit, is numbered bit 31. So 0-based, least significant is 0, most significant is 31. Like I said, that's a pretty common convention, unfortunately not universal. There are some people who insist on numbering bits starting at the left. I don't know what's wrong with them. So when we talk about bits, that's the destination is encoded in bits 0 through 4, we always mean the least significant bits. Another thing about layout that you'll need to remember, which is that this instruction is a 32-bit word. And we're really thinking of it as an entire quantity of 32 bits. So now, how do we actually lay that out in memory? Well, we lay it out in memory the same as we would any other 32-bit word on a little endian architecture. That is, the first thing that comes in memory is the least significant, the lowest order byte. That is the lowest order 8 bits. So when you're thinking about generating this instruction and then stuffing it into memory, the very first byte is kind of this set of 8 bits right here. And that is followed by this set of 8 bits, and followed by this set of 8 bits, and then this set of 8 bits at the end. Very, very important that you kind of keep this in mind as you start generating machine language and then trying to read it back and making sure that you got the right thing. Both the write and the read need to follow this little endian memory layout for 32-bit words. Okay, so registers are encoded in here. There are a couple of special bits at the most significant end. The most significant bit is going to tell you whether this is a 32-bit or 64-bit instruction. A couple bits over from that is a bit telling you whether you're going to set the condition flags or not. That's the difference between an add and an add-s, or adds instruction. Yes? Sorry? Okay, the encoding of the instructions is 32 bits, but the instruction can operate on either 32-bit quantities, the W registers, or 64-bit quantities, the X registers, and that's what that bit means. Great clarification. More questions? All right, let's see an actual instruction. This nasty sequence of bits corresponds to the assembly language instruction add x1, x2, x3. So remember our convention. The destination register always comes on the left of the assembly language instruction. Confusingly enough, it comes at the right of the machine language instruction. Sorry, I didn't make this up. I'm just telling you the bad news. So let's try to decipher these bits according to kind of the pattern that we saw on the last slide. The most significant bit tells us whether the instruction is operating on 32 or 64-bit quantities. In this case, it's a 1, therefore it is operating on 64-bit quantities. So we know that it corresponds to operating on the X flavor of registers as opposed to the W flavor. That bit 29 tells us whether we're going to set condition codes or condition flags. In this case, it's a 0, therefore we're not setting them. Therefore, this is an add, not an adds instruction. Those bits in dark red taken together is the opcode for a 3-register add instruction. In blue, we have the destination register. That's the binary 1. In green is binary 2. That's the first source. In orange is binary 3. That's the second source register. And all of the rest of the bits are 0, meaning there's no kind of additional stuff encoded by this instruction. Okay, so just very systematically go through the bits and decipher what they mean according to this general pattern. Or going the other way, if you need to generate the machine language version of an add instruction, start creating it bit field by bit field. And in fact, for assignment 6, we're going to have you fill in a special instruction, a special function in C that takes a particular numeric value and stuffs it into a set of bits in an instruction. And that's going to be very, very convenient for creating instructions like this, one set of bits at a time. Okay, questions on this? Yeah. The opcode basically consists of these red values right here. So if you look at the full reference, they're drawn in a very similar way to this, where it basically just says this set of bits taken together tells you this is an add instruction. All right, let's move on to something a little more complicated. The next class of instructions that we're going to look at is instructions that have an immediate value. That is, instead of having 2 source registers, they have either 1 source register and a constant, or they just have a constant and a destination register. So 2 different layouts, memory layouts, machine word layouts for those 2 kinds of instructions. And again, there are fields of 5 bits at a time that tell you the registers involved. But then there's a big, long set of bits that you can use for an immediate value. And in fact, the variant that has only one destination register and no source register allows for more bits to be included in that immediate value. So you can have a greater range of immediate values that you can use with that flavor of instruction. So here is an example of a subtract instruction where we have a single source register, an immediate value as the second operand, and a destination register. So again, we march down all of these different fields, and we try to figure out what they're telling us, or what they're telling the hardware. Most significant bit is a 0. We know this is going to be operating on 32-bit quantities. Bit 29 is a 1, so we're setting the condition flags. So we know this is a subs and not a sub instruction. We have those red numbers, those red bits. Together they tell you this is a subtract involving a source register and an immediate value. So subtract immediate. In blue, we have the destination register. That is register 1, and because we are operating on 32-bit quantities, this is W1. In green, we have number 2, therefore this is W2 as the first source register, the first source operand. And in orange, we have a bunch of bits that together tell you that immediate value. So in order to interpret that, you have to start, counting exactly which bits correspond to that immediate value, extract that as a binary number, convert it to decimal, and understand what it is telling you. So in this case, we have a bunch of zeros, 1, 0, 1, 0, 1, 0. Calculate that out. That corresponds to 42 decimal. Okay, so systematically, you can go through the fields, figure out what they mean, translate back to an assembly language instruction, or go the other way. Construct an instruction that does this subtract by stuffing into that binary word fields corresponding to the 2 registers and the immediate value. Yes? So the assembler sometimes does stuff behind your back, and sometimes it will just tell you, I can't do that. I actually don't remember in this particular case exactly what it's going to do. But it's going to do one or the other. Either it's going to construct some instructions behind your back and kind of construct that number you're trying to subtract, stuff it into a register, and actually subtract a register, or it's just going to tell you constant too large. I encourage you to try it out. None of the examples that we're asking you to code up actually push the limits of how big an immediate value you can use, but there are these limitations. So try it out, report back, tell me what it actually did. I've seen assemblers work both ways. All right, let's look at an example of an instruction without any source registers. So this is one destination register and just one big immediate value. This is a move immediate instruction. And basically, how to include everything I said on the last slide with the exception of the source register. Works exactly the same way. The interpretation of the other bits is the same. Let's look at branches. So as I said, there are both unconditional and conditional branches. And the conditional ones are different because there is a set of bits dedicated to telling you which condition that you're using. And of course, that cuts into that immediate value that is stored in the instruction. Check 1, 2, check 1, 2. Yeah, that sounds better. All right, what do we mean by an immediate value in a branch instruction? Well, it's telling you where to branch, but how is that actually encoded in the instruction? Is it the address of the instruction you're branching to? It turns out that no. What's actually encoded here is not the address itself, but where you're branching to relative to where you are. That is, it's an offset that is stored in all of these branch instructions. So it's branch 10 bytes later, not 10 because that's not a multiple of 4. Branch 12 bytes later, branch 40 bytes earlier. It's a signed, so both positive and negative, signed offset of where you're branching to relative to where you are right now. And that multiple of 4 thing is interesting because it's enforced, and it's enforced in a very interesting way. We know that the current instruction is somewhere that's a multiple of 4. We know that the destination instruction has to be somewhere that's a multiple of 4. Therefore, the offset is a multiple of 4. Therefore, the binary version of the offset ends in a couple of 0 bits. Therefore, we're not going to bother to store those 0 bits. So that's a kind of interesting feature of these branch instructions that you have to take into account, both when you're interpreting what they do and when you're constructing one of these branch instructions. So let's look at the most basic flavor of branch. It's just the B branch, unconditional branch instruction. Let's try to interpret what this instruction means. Well, those first 1, 2, 3, 4, 5, 6 bits is the opcode, unconditional branch. And the rest of the bits correspond to a signed offset where we're not storing the last 2 bits. So we look at that number, bunch of 1s and then 0, 1. We interpret that as a signed 2's complement quantity. It turns out that it's the signed 2's complement version of -3. If you can't kind of stare at that and realize it's -3, go through the algorithm, basically flip all of the bits, add 1, and that is the negated version of that. So this is -3. But we have to add an implicit couple of zeros at the end. We have to multiply that number by 4 in order to figure out the true offset. And so the true offset here is -12. So this instruction says, whenever you encounter this instruction, branch 12 bytes earlier. Or you can think of this quantity as a number of instructions. So branch 3 instructions earlier. Okay, equivalent way of thinking about it. Questions on this? This is one of the trickier aspects of this machine language. All right, what if you need to do a branch and link? Well, same deal, different opcode. Very simple. What if you need to do a conditional branch? Well, there's this other instruction format where you encode which condition you want in some bits. The actual offset is a little bit shorter. You're more limited in conditional branches than in unconditional branches, but it still gives you kind of plenty of range. You still have, what is it, 16, 17, 18, 19 bits worth, so that is plus or minus 256,000, but you multiply by 4, plus or minus a megabyte. So still plenty of range in where you can branch to. Give or take a factor of 2. Can't do arithmetic at 10 a.m. And you look up in your handy-dandy decoder table that you find in the instruction set reference of which condition that is, and this is a less than or equal to. Okay, so conditional branches. Loads and stores. These, are sort of along the same lines, except that there are two different flavors to account for the different addressing modes that we've encountered. So remember that we talked about addressing modes where you can add two registers and then dereference, or you can take a register and apply an offset and then dereference that. So those correspond to these two different flavors of load and store instructions. There's another difference here, which is that we now have 2 bits for the data width instead of just 1. So all of the operation instructions can only operate on either 32 or 64-bit quantities, but loads and stores can actually operate on 8-bit, 16, 32, or 64. And so we actually need 2 bits to specify the width of the data being manipulated by this load or store. All right, example here. Here is a load instruction using the 2-register addressing mode. So here we take register x1, encoded here, and register x2, encoded here. We add them together, dereference that, and then we load 64 bits from the resulting memory address and stuff the result in register x0. Okay, everybody sort of see how this works. Here is a register plus offset addressing mode. So we take the stack pointer register, wait, which number is that? Well, it turns out that stack pointer is the same as register x31 for the purposes of this instruction. So we take the stack pointer, we add 12, including this implicit shift. The implicit shift here depends on the width. So this is a 64-bit, so the implicit shift is by 3 bits. We add those together, look up in memory at that address, stuff the result back in register x0. What if it is a store byte? Well, we set the size, the width of the data to zeros. We now don't have an implicit shift of the offset, so we actually need to encode 24 as 24. Here we still have the stack pointer and the destination register. Starting to get tedious, ain't it? One more that we need to go through, and this is kind of the one that makes the least sense to me, sorry. It's the ADR instruction. Load the address of a memory location into a register. Again, this takes an offset relative to the current location in memory. So load the address of the variable that lives 17 bytes before me. Okay, that's how you should interpret ADR. Now here's the crazy part. It's where that offset lives. Don't shoot the messenger. Some of the offset lives here, and the rest of the offset lives there. Sorry, it's just the way it does. So this gives you the two low order, the two least significant bits of the offset, and this gives you the rest of the offset. So if you have an instruction that looks like this, in order to figure out where that is in memory, you have to take these bits in orange right here, concatenate them with those two bits right there to get the complete offset, and now add that to the location of this instruction. So this instruction says, load up the address that's in memory 50 bits following this instruction and stuff it into register, whatever that is, X19. Sorry, just the way it is. Questions on this? So you'll be happy to know that you can wake up now, just in time for your next class. These are basically the instruction formats that you're going to need for assignment 6. Like I said, use the slides liberally as a reference. And happy hacking. See you next time. Now you can come back.